Folks, good morning. We're ready to start our training. It's a technical presentation, and I'm very happy to be joined today by my colleague and friend, Mr. Steve Howard from Perforce. Right now, you have probably taken a breath in the last couple minutes. You probably had some water, coffee in the last 24 hours. But really, those are mandatory. So often in software, we focus on requirements, design, coding, and testing. Well, folks, static analysis is the oxygen and water of life for safety critical software. We're going to find out why in this fast-paced session. It's going to be about 45 minutes, mostly Mr. Howard giving you really valuable details on static analysis. And then we're going to have 5 to 10 minutes of questions and answers, okay? When you have questions, we've muted you just to keep everything fast-paced, but we want to hear your questions. So simply write your questions in the dialog box. See that little question box there? You can write your questions at any time. We'll try to get to them all. If we don't, we'll follow up by email, okay? So with that, let's begin the essential first step to certified software, and that's aviation, automotive, nuclear power, rockets. This iPhone, is it critical? Help, fire. Now it is. So critical software, all software is critical. We're going to have a quick introduction and then a 5-minute overview of certified software. Then we're going to talk with particular challenges and solutions by Mr. Howard from Perforce for certified software code analysis and static analysis, and then go into our question and answer session. Now, about AFuzion, you probably know about us. We're the world's largest aviation-based safety critical solutions services company. We've got about 60, 65 engineers now worldwide that help clients optimize their processes for DO-178C, ARP, 326, all the alphabet. We do software system engineering. If you see a plane flying, almost certainly it has our solutions in it because we work for 95% of the world's largest companies. They use our mentoring training, our out-of-the-box templates and checklists. At Perforce, you've probably heard of also. They deliver really leading-edge projects that span the entire demands and life cycle of DevOps. They bring imaginative solutions to life more quickly, securely, with outcomes that can change your business. Over half of the Global 500 rely on Perforce to make their business successful, move it forward. They collect they have a collection of 1,700 DevOps experts worldwide. They solve problems and seekers in 80 countries, 16 offices worldwide. They're even larger than AFuzion. With that, what is certified software? Well, in one slide, slide 4 here, oversimplified, we start with high level, top level requirements. They're our foundation. They cover the full system, and a cell phone is a system, flight controls, landing gear, the bathroom lights, the automotive hydraulic braking. Then we have detailed low-level requirements. Those are the final details. They're unambiguous. You can verify them. We should be able to give these requirements to 2 different teams worldwide, and they create different solutions, different design, different code. But from the black box, the outside, all the tests pass. It's equivalent. Well, that means we need determinism for data flow, control flow, who calls who, what are the internal, external interfaces that design architecture, and then the implementation. We're going to have top-down and bottom-up traceability, closed loop, to ensure everything's satisfied, all the requirements, design, architecture, constraints, and nothing extra. We're going to meet all the requirements. We're also going to meet a coding standard. Now, class, we're going to meet requirements and a coding standard. That's why you're here today. Think about this. Certified software. You are humans. I am human. In a couple of years, I'm going to have an AI presentation. You're going to think it's Vance. It's going to be an AI, but not yet. not for safety critical. Humans are great at assessing requirements. We're the best. But we're the worst at assessing code. Oh, I know. Each of you thinks you're the best. It's the other person. Yeah, you got it. The real solution is to realize that humans are subjective. We have different skill levels. But static analysis tools, especially qualified static analysis tools like Perforce, they are not subjective. It's the solution. Because, remember, meeting the coding standard, humans are bad at this. Computers are great. So think about that. We all know that everyone, Microsoft, Apple, Boeing, Airbus, Audi, Porsche, Tesla, they do human-based code reviews. But humans are generally less familiar with the intricacies of that code since they didn't write it. Manual code reviews are completely subjective. Coding standards have 100, well, many more than that, major rules, but thousands of minor rules. Can you, as a human, keep all of those in your brain, Mr. Ms. Einstein? Manual code reviews, they're not repeatable. FAA, EASA here, we hate them. Yeah, so do I. Good quality manual code reviews, when you have them, they take a lot of time. We find at AFuzion, we're pretty fast, but even us, it takes us at over an hour to review 30 to 50 lines of code. It could be more if it's complex code. So folks, you're all smart. You tuned in to this webinar. Do the math. Human reviews simply do not compute, okay? Well, folks, that's where static analysis comes in. So think about that. Yeah, think about that. Mr. Howard is now going to present from the Perforce viewpoint. Rock and roll. Steve, you are now the presenter.
Thanks, Vance. Let me just share my screen. So it's just waiting for it to come over.
Very good. We've got a good crowd here tuned in today. So a lot of folks interested in your static analysis.
Yeah, thanks. Have you switched it to me because it hasn't come up with my offer to share yet?
Oh, okay. Let me make sure I've done that. Oh, okay.
Thank you. I guess you're working on it now. So static analysis, just to give a brief introduction whilst Vance is changing things over, is the idea of analyzing computer software without actually executing the software in any way, hence the static. So this is something that we can use to glean information from the software program. And that can be in many different forms. I mean, it can be anything from license compliance through, lots of different forms of static analysis, through to coding errors and compliance to standards, as Vance mentioned. So we're going to talk about mainly those latter two today in terms of the purpose. But essentially, this automated examination of the software can also be run prior to the program actually being run itself. We can determine some of the information from the code very quickly and early in the cycle before we have something that even compiles potentially, and certainly before something can link. Static code analysis, so we talk about static analysis generally, but static code analysis is when we're applying the static analysis to the source code itself, and that's generally what we're going to be talking about today. That's what we do, as opposed to an analysis statically of the binary code, if you will, at the end of things. So we're talking about the source code and analyzing that. You sometimes also hear this term static application security testing, or SAST, which is occasionally used rather than the more generic static analysis or static code analysis terms. But essentially they're all the same. It's just depending on what we're specifically looking for. In the case of SAST, it would be security type issues. So static code analysis, or static analysis, has evolved somewhat over the last 50 years, in fact. Originally, obviously, the concept of linting arrived with us thanks to Stephen Johnson back in the very late 70s. And that was a basic idea of checking for structural issues that look like mistakes, simple coding mistakes, if you will, at the level of the translation unit. But in the sort of late 90s, early 2000s, things really started to evolve in static analysis, and it became much more than that. And actually, now we have these tools which are able to essentially simulate control flow and data flow through the entire system, and in an interprocedural manner. So it's actually looking at the whole code base as one, and essentially looking at how it would behave when all put together. And in fact, things have evolved further since then, where we can now use those same algorithms, but do it on a kind of partial basis. So we can have performed one set of analysis on maybe the baseline of the code, and then we can actually look at the same interprocedural analysis on just a small subset that's being worked on in a CI pipeline, for example. So we'll talk about that later on. But essentially, all of these are the same. It's just gleaning extra information and then being able to do that more quickly. So simple structural analysis, what we had to begin with, is something that generally a hawk-eyed code reviewer or even compilers nowadays will often report. So we're talking about, again, simple mistakes like assignments in conditions, suspiciously placed semicolons, maybe where we've accidentally closed the if condition before we've actually had the body of that if that was intended. Variables that are uninitialized on declaration. Of course, they don't need to be initialized on declaration. They can be initialized as long as they're initialized prior to use, then maybe that's something we would want to detect. But the simple case would be, let's make sure all of our variables are initialized on declaration, and then we won't have a problem. So that's what we kind of started with. And coding standards as well kind of evolved to fit around those limitations of only having this kind of analysis. And they were very strict, very rigid, and they weren't necessarily well tuned to really finding the important issues. But this is what we had, so that's why those coding standards evolved in that way in the early days. Once we had interprocedural control and data flow kind of analysis, we were able to find a lot more. We're able to find a lot more interesting issues, if you will, things that we now would really struggle to spot with the human eye. It is possible to spot some of these with the human eye just by looking at common mistakes like the use of memory, perhaps without a prior check for the memory being valid. But those kind of things are much harder to see in a very, very large system with many, many calls to different submodules and so on and so forth. And all of that complexity often obfuscates us from being able to really see the issues. And this is where an analysis tool really does a great job of helping us, because it can very quickly spot those links and spot those problems across very, very large code bases, picking out the things that really matter and presenting them to us to actually review. And other classes of issues that fall into this set would also be things like buffer overflows, tainted data from a security perspective, even concurrency violations, if you will. And many of these issues traditionally, and certainly back in my day when I was working in the aviation sector, we used to find these kinds of problems with dynamic testing. This is how we would detect things like buffer overruns and so on and so forth. We didn't see them necessarily in any other way. That was how we found them, unless they went out into the field, of course, in a very terrible case. So we kind of evolved the tools for static analysis, but also the coding standards then that we could use to apply to those code bases where we really had safety at its heart. Programming languages such as C and C++, of course, they have clearly documented areas of unspecified and undefined behavior. So that in itself gives us some complexity to deal with from a safety perspective. And also different compilers may implement and actually have the right to implement the language in different ways, and subtly different ways that aren't always easy to spot. This makes, multi system or multi-platform builds for our software very complex in terms of being able to spot the issues that might exist in one system but don't in all of the others. And so really the coding standards that evolved first were trying to prevent the use of these riskier language elements or keywords and constructs that actually weren't well defined or had some flexibility in the way they were actually implemented by the compilers. So it was an obvious first thing to make our code more secure, more safe. And actually coding standards then evolved further because they really capture experience of developers that have been there before and seen the issues that we've created in the past. And so we can actually also not only use them to restrict the language usage to a subset that is not using any of the unspecified or undefined behaviors, but also to use the generally safer behaviors, and things that are not so safe to use, we can exclude. So this then means that we have code written in a way that minimizes ambiguity and maximizes the clarity of the code, and hopefully reduces the probability of introducing any kind of coding errors. And certainly this applies with many of the common coding guidelines. So MISRA and JSF, for example, are prime examples of this. The original MISRA standards, MISRA C, back in 1998, was very much focused on that first requirement of making sure we didn't have unspecified and undefined behaviors, and also making sure we weren't using any less safe areas of the language. Unfortunately, that also included things like dynamic memory. Dynamic memory is something that's quite important if you're working in any kind of larger system. And so whilst it's clearly very safe to not use it because you can't have problems with it, it's also very restrictive. And so those standards have really evolved to be more targeted. So you can use those additional language features that you may wish to or need to use, but we use them in a safe way. Often it's much easier to justify the use of a well-known standard that's well recognized, and for example, MISRA or JSF, bar C, there's lots of them out there, and then have exceptions to that. So you're applying a subset of that and justifying why you're turning off some of the rules, rather than trying to create your own. Creating your own standard from scratch is not only a relatively arduous task, but it's also one that then takes a little bit more work in terms of the justification when it comes to signing off on our project. Coding standard compliance is the idea of making sure that you're following the standard. And in the case where you're not following the standard, justifying why that is what's happened. So we have this concept that a coding standard rule set is checked. The rules are checked throughout the software for any violations. And a violation means that we have an instance where we have not followed the guideline, and we have a case, an example, it's not compliant. When we have a non-compliancy or a violation such as this, we can apply a deviation. For most coding standards, they have a mechanism for applying exceptions to the rules, essentially. And those could be at the rule level, or they could be at the individual instance of a violation level. Generally, we would need to show a compliance report to prove that we're compliant to the standard. And this will generally entail something along the lines of what we see on the screen here, with a table documenting the rule itself for each rule within the standard. Maybe it has some category. In this case, we're looking at a MISRA example, so it has the categories of required and advisory rules. We have the violations, where we have open violations of the issues. We have to, of the rules, and we have to deal with those, or we have to apply deviations. And a deviation would then give us an acceptance of a certain instance, or particularly an overall rule. And once all of that's calculated, we will have for the standard a compliance level for each one of those rules, and therefore a compliance overall as well. So all of that information is generally captured in what we call a compliance report. The beauty of static analysis tools is that they can produce these reports generally automatically as part of the whole process. So it makes it very easy to see that we're compliant or otherwise, and if we're not compliant, then to know why not. So how does this all tie back to functional safety, which is where we started? Well, as Vance pointed out, functional safety standards, they require a lot of checks of each of those levels as we go up the right-hand side of the V model with respect to the code that's been created at the point of the V model. And really the whole purpose, of course, is to try and minimize the risks associated with the development and the design of the product. And so we generally have rules that we have to comply with from the functional safety standard itself. Many functional safety standards require the use of a coding standard, which then means that we have to define, follow, and enforce that coding standard. And that means essentially to comply with it. DO-178B or DO-178C are examples of functional safety standards that require it, but there are many more, including the standards for automotive, medical systems to some extent by extension of the use of 61508 there, general electrical systems and so on, and is recommended in many standards anyway, even weaker safety or mission critical standards in terms of general good practice. Once we've met the requirements of the functional safety standard, if we've done that using tools, it's important that we're able to show the tool is qualified, of course. So the use of a tool and the development of a certified project requires that the tool is qualified itself. In other words, we want to make sure that the tool itself can be trusted to give us reliable results and that it has been developed with clear requirements, test cases to show that the behavior has been reviewed against those requirements, and then test evidence as well. So we said the tool or tools have been qualified for use on the project. Tool qualification can be done manually, although that's very time consuming and quite difficult, or by using a kind of pre-qualified tool, if you will, one that can be qualified easily with the relevant documentation and test cases that we can run on our own system. So a qualifiable tool or qualified tool is quite important. And then it's worth just mentioning security. So here we have talked about coding standards and safety. And you could ask, what is safety if we don't have security? And in many systems now where we have connectivity to external systems, it's important that we not only protect our own system itself against unexpected behaviors, but also against external influence using intended behaviors for unexpected requirements or cases. So in other words, even a safe system, if we had unauthorized access or manipulation from outside, could lead to dangerous situations. So there are some coding standards out there actually that apply specifically for security, and there are some which apply for safety and security, such as MISRA-C. The ones that apply for security only would be things like the CERT standards, CWE, although that's really more of a catalog rather than a particular coding guideline, the DISA STIGs, and also OWASP, which applies for more web application security. But all of those standards essentially could also be applied, and in many cases actually overlap significantly with some of the safety standards like CERT and MISRA, for example. So great. In some cases, we need to use static analysis, or at least it makes life quicker for complying with coding standards, and that's an important thing. But there are other areas where static analysis can also help improve our developer efficiency, making sure that we're not wasting time and getting to market much quicker with our products. We all have a shortness of time when we're developing anything. In fact, if we look at Capers-Jones research on this from the idea of generally where defects are introduced from a coding perspective and where they're then detected, and the cost of detection or repair. It increases very rapidly as we move through the software development process, all the way up that right-hand side of the V model and beyond, of course. And probably these figures are not true in terms of the cost post-release for some of the systems that we're working on in safety critical software, of course. So the idea being that the majority of these issues are actually caused at the coding level. That's where they're created. And the tests are there to catch them generally as we go through the cycle. Of course, static analysis is a kind of a form of testing. It's an automated test run of some sorts. It's not against requirements, but it is testing the code against something, testing the code is correct in terms of some of the behaviors. So a question of where static analysis is run in the cycle also applies in this time map. So static analysis can actually be used at all stages of the development lifecycle, essentially. So through the implementation phase, we can use the tool very much, or the tool static analysis as part of our desktop environment. Once we've committed that change or changes, we can run CI jobs that immediately scan for changed code causing new defects. And of course, we have at the end of the process, before we finally release, hopefully, or even before we perform our final testing, we can perform what we call full baseline scans of the whole program as one, making sure that we have compliance to that coding standard set or the other requirements we may have for quality. These days, a lot of this falls to CI/CD processes. So if you think about sort of the general idea of multi-branch development, in this case, I've taken the example from GitLab. They think of it as having a world of where you have a baseline master running along the bottom, and the feature branches are then splitting off from that and merging back in once they are complete. Along the feature branch, we make our changes, we run our CI pipeline, we review the changes that have been made, maybe a peer code review, approve the changes, and finally merge. And once we've merged, we run the CD pipeline to bring everything together. This is classic continuous integration, continuous deployment or delivery. Static analysis fits in very nicely. So at the end of that cycle, of course, before we release or before we go to our testing, we can actually perform the full baseline scans to make sure everything is compliant and we've weeded out as many of the coding issues as we can. But we can also shift left and bring things to the CI pipelines, bringing them further left in the cycle, saving time and money and rework. So that effect is essentially what Capers-Jones shows here. Essentially, we're moving the detection of issues to the left and therefore making the cost of repair much cheaper, saving time, money, and rework later in the cycle. So essentially, our continuous integration now becomes continuous compliance. And with every commit or with every merge request, we can be making sure, enforcing, there are no new issues entering our code stream, no new violations of our standards. For example, again, using GitLab, this is what it would look like. So we have a merge request on a feature branch, and the merge request has blocked because of new issues, not because the build failed in this case, but because we've detected new issues that weren't there previously, new violations of the standard or the requirements from the coding perspective. We can go one step further though. So we've obviously talked about the baseline scans where we get the final reports of compliance. We've got the Delta CI scans where we're looking at the differences on the feature branch, but we can also perform analysis in the desktop environments as well. And really this then gives us optimal shift left because we're checking that issues are removed before we even commit. And so generally this does two things. First of all, it even further shifts left the defect detection process, thus making it even cheaper to repair. But it also tends to have the impact that the developers themselves are more aware of coding. We're finding things straight away. It brings them into the whole process. They learn the coding standard because it's there in their environment as they're writing the code. And so we actually introduce less issues in the first place during that coding phase. So it's a very positive effect on the overall results. It saves us a lot of time in testing downstream, and it saves us a lot of rework, which of course then causes more testing. And this is what that would look like. So this is an example of our desktop analysis scans running inside Visual Studio Code, detecting issues. What about legacy code? So one of the cases that we almost always come across is that the code is already written. Code is largely created, or we have a legacy system we're using as the basis for a new project that we're working on. It's a barrier to using static analysis in that when you first run your analysis, of course, you don't get a clean bill of results very often. It's normally going to be the case that you have a backlog. So how can we deal with this? Well, first of all, sometimes systems have already been released and have been working in the wild and out there in the world for many years without issues, or at least with issues that we've then subsequently resolved. So when we perform our first analysis of this system with a new tool, with a new coding standard, and we find violations, yes, we could fix those violations, but that might actually introduce more risk to quality, given that the system has already been running out there in the world for so many years very successfully. So we wouldn't necessarily recommend that. In other words, if it isn't broken, don't fix it. And what we can do is actually apply a baseline. So instead of having to deal with that backlog of issues from day one, which would somewhat turn off our developers and potentially introduce a lot of risk to the overall quality and safety for the future, the idea is that we actually simply zero those new issues, put them in a holding place for the time being. It's useful data to have in case we ever find issues in the future that relate to them, but it's not something we necessarily need to fix now. So what we then have is this baseline of data that we're not dealing with now, but we are dealing with any new issues that are introduced from that day forward on any new or changed code relative to that legacy system. And we can detect that very conveniently. And of course, the baseline can move forward as well if we need it to, if other things merge in and so on. So what about the comparisons? Going back to what Vance said at the very beginning, what about the comparisons between static analysis and other technologies for analysis and testing and the process of those right-hand side tasks in our V model? Well, manual code reviews, as Vance said, in fact, are very good for verifying things like code intent. And also human intelligence applied to specific cases that they spot is invaluable. We cannot really improve upon that when it's done well. But what it does leave us with is a lot of code that perhaps we're not focused on. At any review, we'll always typically focus on some specific issues, some specific failings that you expect to see, or things of concern with that kind of code. And that's great. But what it's not giving us typically is a very clear, full coverage of all of the code and all of the rules. Static analysis through a machine obviously is very efficient at doing exactly that. It will look at every piece of code and apply every single rule that we have in our rule set. And some of those rule sets, like MISRA, for example, are around 200 different rules, and each rule has multiple subcases, as I think Vance mentioned. So this is a very big task for any human to keep in mind. Static analysis is also relatively inexpensive. It's very fast. It's not dissimilar from the time it takes to compile and link the code. It's automated. It's complete. So static analysis doesn't really replace manual code review, because there are still benefits, of course, from having human reviewers, but it very much complements it and certainly improves the efficiency of that process. The human reviewer can maybe focus on the results of the analysis as a guided code review to help them find some of the key issues, whilst knowing what to look for in very special cases. And what about versus dynamic analysis? As you say, some of those issues that we can now detect with static analysis around interprocedural control data flow type errors, those are the things that we would traditionally find with dynamic analysis. And dynamic analysis, we know, will find issues. And of course, it ensures functional correctness to the actual requirements, which is very important. But static analysis brings other benefits. Again, it's very fast and it can be used up front, weeding out the issues that we would have found with dynamic testing before we've written the test. And that saves us time if we have to rework the code, especially if it's white box testing. It also means that we test the unexpected paths. So dynamic testing, functional testing is very good at testing the requirements and the things that are supposed to happen. It's not as good with the human writing those tests at detecting the things we didn't expect or didn't think about. Whereas static analysis will run all of those negative test cases essentially and all of the unexpected paths and the error conditions as well as the positive conditions. It's running everything. So really there are again benefits to both. They are complementary, but static analysis can be used earlier in the software development lifecycle to weed out the issues that would be found downstream, thus saving us a significant amount of time and pain in any dynamic testing rework. So with that, just to bring things together, ideal static analysis solutions, of course, they need to ensure safe, secure, and reliable code, and we do that best by finding all of the potential defects, of course, with low false positives. If we have false positives, it tends to mean that people are less interested in looking at the other issues. So it's a very important thing that that's always minimized. Generating compliance automatically against the coding standards eliminates any manual paperwork and manual mistakes, of course, and really make sure that we have coverage of those standards documented and clearly documented. Being able to build them into our CI/CD pipelines means that we can continuously monitor the code, looking for changes as they're made on those feature branches, and really just seamlessly integrates them into the DevOps tool chains, making the manual tasks redundant. And the last two really work together in terms of the benefits for the developers. So with analysis tools that can also run in the developer desktop, particularly if it's automatically set up and connected to our central analysis systems with the requirements for the rules and so on already defined, that means that the developers will get rapid feedback on the issues within their IDE as they're writing their code. And that really helps to train the developers as they work, meaning that they really get to understand the standards they're working to and are able to write quickly better code going forward. The Perforce tools, QAC and Clock, were both static analysis tools, both qualified for use in the mission critical, safety critical systems like aviation, are both intended to cover all of these main points. So with that, I'm going to hand back to Vance at this stage, and we're going to have a look at some of the questions that have come in the meantime. Vance.
Fantastic, Steve. That was really terrific. We've got a good number of questions, in fact. So let me go ahead. The first one, is there a recommended coding standard for aviation projects? I know the answer.
Good question.
Let's go for you.
So I'd love to hear your answer as well, Vance, on this, obviously being your specialist market. But yes, there are a number of standards that will certainly work. I don't believe the aviation standards, thinking through all of them, actually have any prescriptive definition of what they recommend, whereas some of the other standards like automotive do. In that case, they recommend MISRA C or C++, for example. But in the case of aviation, obviously MISRA would be a prime candidate, I would suggest, but there are others because of things like the JSF standard as well. But what's your take on that one?
That's a great point. And anything that's subjective is generally left out of 178.254 ARP. The idea being it's subjective, so how can you really objectively evaluate it? DO has objectives. Well, which coding standard is kind of subjective, but we do have a need for 3 standards in our objective world to make things objective: a requirement standard, design standard, coding standard. In the coding standard, almost everyone uses the United Kingdom Motor Institute Software Research Association, otherwise known as MISRA, back in the day when the UK actually made cars. Sorry, Steve, just a little
Very true.
You're absolutely right. Next question now, fun one. I'm gonna let you do this one. Are you planning any tools for DO-254? I presume the asker is curious about Verilog, VHDL perhaps.
Yeah, so we don't have coverage at the moment. Our language support is C, C++, C#, Java. So some of those things that we see sometimes in the other systems like medical device and so on. Python, JavaScript, and Kotlin. So we're not in that VHDL world at the moment. So no, not at the moment.
Okay, cool. Another question. What DAO levels are supported by the Perforce tools for 178? DAO A, B, C, D. Let me start, and Steve, you give a custom finish from your standpoint. This is really interesting, everyone. If you're in aviation, there is no difference in coding between level A and level C, even though level A is 10,000, okay, 100 times 100, 10,000 times more reliable. That reliability comes from hardware redundancy, okay, not the development process. There's zero difference, zero, truly. And there's 3 books on 178 that kind of go into the detail. None of them are any good. I wrote 2 of them. There's no difference between level. Sorry, too much coffee. My God, I got to go cut down on the coffee. 4 cups is a little ridiculous. Now, there's no difference between level A, B, and C software. Think about that. What do you got? We got coding standard. You got data flow. You got control flow. You got low-level. There's no difference. The difference is in the verification, the decision condition coverage, the independent reviews, the MCDC, but not the coding. So for level D, D as in David, you don't need code. And there is no coding standard. If there's no coding standard, you don't evaluate it. You can write the code, hack it, worse than Microsoft, and certify it in the backward fashion level D, because level D is the bathroom lights, exactly where Microsoft belongs. So Steve, go ahead on the tool hall outline.
Yeah, absolutely, exactly. So we with the qualification kit we have, obviously will cover you for all of the levels, but realistically that's A to C, and there is no difference indeed.
Okay. Paul asks, how easy is it to tune a static analysis tool to a corporate coding standard? Ooh.
Yeah, so that's actually relatively easy. So depending on the standard itself and the kind of rules you have in there, whether it's including other rules from other standards perhaps and just renaming them, that's very trivial to do, or creating your own requirements for specific rules that apply to that organization's developments, like a coding standard for the naming conventions, for example, or in some cases also at the project level, where we know about certain risks, and we see this a lot with security actually, where we know that there's a certain attack vector from the outside world and we want to guard against certain types of data or requests coming in on that. We can actually create rules specifically for that. So actually, yes, it's relatively easy to tune the tool to do that instead of or in addition to things like the existing coding standards. You can, for example, have your MISRA standard as well as your corporate naming standard or naming guidelines or whatever, and they all just get checked at the same time, and it's very neat and very efficient.
Okay, cool, Steve. Next question. It's kind of a long one from Gabrielle. And Gabrielle, I know you. Glad you joined today. Gabrielle asks, I need to certify software that currently is running inside an OCI container, Docker. As far as I know, if we want to certify the software, the runtime daemon of the Docker should be certified as well. I have seen some software in the aviation field running in other kinds of hypervisors, for example, VMware, and I know that these hypervisors, either VMware or Docker, are not certificated. So What is going on? How can that be explained? Is it an issue related with the dial level? You want to do that one, or you want to?
Well, certainly. So from the code perspective, yes, we can definitely analyze that code as part of the, within a Docker container, for example, if that's being used as the development process. So in other words, if we do get it sometimes where funny compiler tools actually spawn a Docker container to Docker image to actually perform the build of the code. And at that point, we can also do the analysis. So from that perspective, and then obviously push the results outside before the container is destroyed at the end of that process. But I think that one's probably more on your side in terms of how does that actually get the overall compliance that you need, including the Docker.
Yeah, thanks, Steve. Good reply. Great question, Gabriel. It's a gray area within 178. And in theory, we should really make 178 2,000 pages. 178 DO-178 is the aviation guideline or standard, if you will. We should make it 2,000 pages to cover great questions like this, but we don't. So instead, we put some of the answers in a companion document, the frequently asked questions, and a few of the answers known as DO-248, but even that one doesn't cover this one. Gabrielle and everybody, this is a gray area, okay? It's similar, akin to compiler libraries, okay? If we have a simple library like the sine function or the tangent function, we can calculate arcsecant, right? So do we certify arcsecant? Do we certify them manually? How do we do that? Well, that's a gray area. In theory, now remember, whenever you hear someone say in theory, they're about to exaggerate or lie to you. So lawyers and politicians are very good in theory. So in theory, we should be able to certify by the effect of the hypervisor, okay, the Docker, the socket external software, by checking the effects and making an inference using a definition of equivalence class and runtime instances within 178. But it's really not true. There are behaviors that are not fully assessed. Without doing a code review, data flow, control flow, coupling analysis, and really MCDC coverage down to DAL A, level A, criticality level, the highest level, 10 to minus 9 on part 25 large aircraft, you don't really know for certain, okay? So to be safe, you should simply certify the software, but almost no one does, okay? Interesting. And there's no plans to change that in DO-178D for the future. So I'll probably be retired by then. Next question. Let's move along here, okay? And let's see. Scrolling down, see what. Oh yeah. Do Clockwork and QAC support Ada, C, C++, and how about Rust? Ooh.
Oh yeah, that's a great question. So not Ada, actually, at the moment, to be fair, that's not a language we cover. But partly, I think that was because originally with Ada, there was less way to make so many mistakes. And I think, C and C++ really were a natural field to start with when we were creating things. So yeah, C, C++, I can't remember what else you said there, but Rust is another language that is coming along in the same kind of theme and may replace some of the Ada perhaps in the future. We're hearing in some of the markets we're talking to. But it's certainly creeping into those C and C++ projects already. So yes, Rust is not currently supported, but it will be as of our first release of 26. So it's on the way.
Cool. And last question we have time for, are your Perforce static analysis tools qualified for DO-178C? And Steve, I think that would probably imply DO-330, the tool qual guideline compliance, which is copied from, okay, yeah, actually by ISO 26262 for automotives, right? So,
yeah.
Interesting. Go ahead.
Yeah, DO-330 indeed, yes. So that is the standard now we refer to in terms of our qualification, and yes, they are both qualified for that. So DO-330 qualification kit's available. Yes, sir. And ISO 26262, by the way.
Awesome.
By the by.
Awesome. We have several people asked if we make the training slides available, and that's an interesting question. We do not. And the reason is copyright and American law. When we make slides available, we're almost, not quite, inferring a release into the public domain. However, we're going to send out a link to the recording, so all of you can watch the recording, including the initial banter we had at the beginning. So thank you, everybody. I think a couple of you are coming to our training next week. We've moved that training, well, we've added, sorry, to recorded training. So all of our trainings on the AFuzion website, including these topics for tools, coding, there's 30 topics. They're all available in a recorded format. So you don't have to travel to these horrible countries like Madrid, New Zealand, Tokyo, Berlin to do the training. You can do it at home. Steve, truly a pleasure having you and the team. Thanks for all the hard work, everybody, and we'll see you next month. I think we're doing a 297 IMA and parameter data item. Woo-hoo, gonna get technical on that one. Steve, thanks so much.
Thanks.
Everybody use static analysis, really. Drink water, breathe air. Perforce is the way to go. Cheers from Vance and AFuzion. Bye-bye.